All right. For the last talk of this wonderful conference, Itamar Vigdorovich will tell us about rigidity and stiffness of arithmetic groups.
Yeah. So first, I want to say that I had a really wonderful 2 weeks, both mathematically. I found many interesting talks, and I learned a lot of stuff. And also, I feel like I made a lot of friends here. And I think it's we should all thank the organizers for this wonderful conference. So let's start. Good. Let's talk about rigidity of arithmetic groups. So we probably all know about the Margulis normal subgroup theorem. So let's just recall that in arithmetic group, you have a Q algebraic group. A subgroup is called arithmetic if it's basically the integer points of the group. The Margulis normal subgroup says that under higher rank, any normal subgroup of your arithmetic group, like basically you have hardly any normal subgroups. Of course, you have the finite index ones and you have finite ones, but besides that, you don't have anything. Today, I want to talk about generalizations of this theorem. 2 types of generalizations. One is to talk beyond the semi-simple case, not just without assuming, let's say, Q simple here. And the second is to talk not only about rigidity pertaining normal subgroups, but also maybe rigidity and the representation theory of such groups, the dynamics of such groups, etc. So first, let's talk about what does it mean beyond the semi-simple case. So, well, we have a solvable radical, and we have we can intersect then with gamma. We get this sequence here. So now this part is solvable. And this part is an arithmetic subgroup of this semi-simple group. So in a sense, if you know the semi-simple and solvable, you know, well, maybe you should do, but not quite, because these things, of course, can interact in a non-trivial way. If you kind of think about like maybe inspired by like Mackey theory, when you want to understand representation theory of a group, but you know the normal subgroup. So what you kind of want to understand is the dynamics of the semi-simple part on the dual of the solvable part. Here's a concrete example. If you're interested in this arithmetic group, you're very likely to want, and you're, let's say, interested in representation theory of this group, you're very likely to consider this dynamical system, SL and Z, on the Pontryagin dual of Zn, which is the torus. And this is a very well-studied dynamical system. So now I want to talk about stationary dynamics. So some people talked in this conference about random walks, and I'm gonna review this. You have a group gamma acting on some compact space X. And I also fix a probability measure on the group. With this data, this gives us a framework to talk about random walks, because you can start with a point in your space, and then apply gamma, and then apply another gamma, and just walk, and where those gamma i's are chosen randomly according to this probability measure. So here's an important definition. A probability measure, it actually was also in David Timo's talk and other talks, and then Tzachi Gelandel's. A probability measure is said to be mu stationary if it is invariant and average. So it's kind of like harmonic, or this equation holds. So let's give some examples. The first basic example is, of course, if you have an invariant measure, it's of course stationary. If you're invariant under every element of gamma, then also you're invariant in average. That's not an interesting example. Maybe the simplest non-trivial example that I like is that if you take the free group and you take a simple random walk, just uniform on the generators, and you act on the boundary of the free group, that is the leaves of this tree, of this calligraph, the Cantor set, then when you apply A, you kind of, the mass moves all the way here. So A doesn't keep there's like a natural measure here, and A doesn't keep it invariant because it takes kind of all this leaf to this area. But then A inverse takes it to the other direction, and B takes it up, and B inverse takes it down. So all in average, everything is invariant. So this is an example of a stationary non-invariant measure. And another example of a very similar nature, which is maybe a bit more suitable to the kind of things we discussed in this conference, is just G or gamma acting on G mod P, let's say on the projective plane, SL2R in the projective plane. This is another example of this kind of dynamical system. This has the Haar measure. It is not preserved by the action, but it is stationary in an appropriate sense. And this is the main definition of today. The action of gamma on X is said to be stiff if any stationary measure is automatically invariant. And the theorem of Furstenberg says that if you take this action we discussed before, SL and Z, so SL and Z acts linearly on Zn, it acts therefore on the Pontryagin dual, that is the torus. And we have this very natural dynamical system. Furstenberg proved that this action is stiff. It's non-trivial. There's no reason you would expect it has to be stiff. What I want to do now, because we're interested in general arithmetic groups, not necessarily SL and Z, semi-direct product Zn, I want to also replace Zn by other groups and maybe even non-abelian groups. So, for example, I can take the Heisenberg group, and it admits a very nice action of SL2Z, the discrete Heisenberg group. And I would like now not to look at this action, but to look at the action of SL2Z on the dual of the Heisenberg group. But what is the dual of an nilpotent group, right? It's not abelian. Okay, so So this leads us to talk about a notion called characters. There's a quite general notion which will allow us to answer this question. So this will be a bit, this is a bit maybe a diverging topic, so I'll do a brief introduction. It's not important to understand all the technical details, but let's just do a brief introduction. If you have a group gamma, general group, a trace on this group is a function, a complex valued function, which is positive definite. If you don't remember what that means, never mind. It is also a class function, and we just normalize it. And like in representations, we have irreducible representations. So the analog here is those the ones that are kind of like indecomposable. We call them characters. What's more important is the examples that we have. So the first main example is if you have a homomorphism of your group to the circle, this is indeed an example of a character. And more generally, if you have a finite dimensional representation and you take the trace of it and we just normalize, that is also an example of a character. I call these finite dimensional characters. What is quite remarkable is that sometimes you can even take an infinite dimensional representation and take its trace. I'm not going to explain now because that will make me, I'll need to go into functional analysis here, but maybe the most important example is that if you take the regular representation of any group, there is a coherent way to take a trace, even though it's infinite dimensional, and this will actually give you the Dirac function of the identity. For finite groups, you probably know this, that the Dirac character corresponds to the regular representations in the Frobenius sense. Anyways, this is character theory. And actually, sometimes people call the space of all characters the Thoma dual of the group, because it really serves in many senses as the dual. Let's see some examples. If gamma is abelian, then this dual is nothing but the Pontryagin dual. And if gamma is finite or compact, you can do this for topological groups too, then this character space, this dual, is just the space of irreducible representations up to equivalence. We're only generalizing classical notions of characters. Here's a first non-trivial example. So now gamma is nilpotent, infinite nilpotent. There's a theorem by Howe, that's actually from his PhD thesis, that any character is what's called centrally induced. more or less, it means that that characters are kind of induced from centers. In the finite group jargon, you should think about like monomial groups. This is the kind of thing you should think about. And let's be very concrete. We're interested in the discrete Heisenberg group. And we want to understand how does the dual of the Heisenberg group look like. And turns out that it's quite remarkable. It's this space. This is the dual of the Heisenberg group. So let me explain what we see here. So first of all, on the right-hand side, this is a function that many times in a first-year calculus course, you have this question, does there exist a function that is continuous on the irrational points and is discontinuous on the rational points? And then the example you give is this function. And you think that, I would think that this is kind of examples you show just like you create those functions just for counterexamples, and I was quite shocked when I studied this space and I found out that actually the space of characters of the Heisenberg group, it's pretty easy to see that it should be fibered over the circle. But what's amazing is that the fibers are all tori, that the size of the tori are prescribed exactly by this function. I won't explain exactly why now this is the case, but this is an example of a dual of a non-abelian group. And like I said, we were interested in dynamics on such spaces or random walks on such spaces. So now it's time for results. The first result is about a general statement about arithmetic groups, about the dynamics of arithmetic groups. So you have an arithmetic group gamma. I'll denote by rad gamma the radical of gamma. Now you can take any definition you have in mind for radical, the theorem will be okay. So the amenable radical is like the strongest form, but you can take the solvable, unipotent, whatever. Now gamma acts on this normal subgroup by conjugation, and this induces an action on the dual by homeomorphisms. So this is my dynamical system I'm interested in. And the theorem is that you take any arithmetic group. Here I don't assume anything, not semi-simple, not higher rank, not anything. Somehow there's enough structure inside the theory of algebraic groups, of arithmetic groups, to ensure that always when the action of gamma acts on the radical or on the dual of the radical, it acts in a stiff way, that there aren't really interesting random walks. The stationary measures are somehow always invariant. Let's see how much time. Yeah, maybe I'll say just a few words about the proof idea. So let's first assume that the radical is actually abelian. That's like SLN Z semi-direct product Zn. Well, this is, I quoted Furstenberg's theorem, and it's not that it's exactly enough, but more or less, this is the idea. You basically just use known results. The next case to consider is nilpotent. So nilpotent, I will use the theorem of Howe to say that somehow all the character theory is coming from the center in order to reduce to the abelian case. So actually in this example, for this particular example, it's very easy to see that the dynamics is stiff because it's really, if you take a measure on this space, it's really fiber-wise measures on tori, and then the action is just fiber-wise, and then you can really straight away reduce to the abelian case. Of course, in the general nilpotent case, it's a bit more difficult. The solvable case is maybe my favorite part because this is the unipotent radical, this is a solvable radical, and this is a fiber. You can restrict every character from here to here, and you get this fiber bundle, and this compact group acts on it. You have a fiber bundle with fibers given by a compact group acting on it, and the dynamics is not just straightforward. It won't be fiber-wise. You get some kind of cocycle. So we use some machinery of Zimmer and actually of Mackey to resolve this case. And the amenable case from the solvable is quite easy. It's just up to finite index things, and you can do this. So this is the idea of this theorem. But of course, what I promised is that all this dynamics stuff should have consequences on arithmetic groups, things that are regardless of dynamics. So this is actually the main result. And here we heavily use work of first by Boutonnet and Udaye, and then of also together with Bader and Peterson, that really brought a nice framework of studying stationary dynamics on arithmetic groups. And we were able to get the following. So assume that the semi-simple part of your group is of higher rank. And let gamma be an arithmetic group. Then gamma is something called that they coined as charminable. It's a combination of the words character and amenable, which is a very powerful notion. And just to demonstrate how powerful it is, we automatically obtain all these theorems. For example, similar to the Margulis normal subgroup theorem, we get that every normal subgroup is either amenable or co-amenable. Every character is either amenable or induced from the amenable radical, and many other statements that I'm not going to say. Maybe I just want to say one thing about representations, which I don't know, maybe it doesn't seem so exciting, but representation theory, like if you take in a reductive group, there's a nice representation theory. But if you take a discrete group, you can't really do unitary representations of discrete group. It's a wild theory. But this tells you that nevertheless, there is some kind of two types of representations. Either they're kind of very small. For example, if you assume property T, these are just finite dimensional ones. Or they're kind of really induced from the amenable radical. They're very large in a sense. So this is the kind of statements you can get. And this is the theorem. And now, in the last time, I would like to explain a bit just about how is this dynamics related. How do you really kind of get those rigidity statements from this dynamics? Because I didn't completely explain it. I gave some intuition. Let's first recall Margulis normal subgroup theorem again. You have an arithmetic group of high rank. Then every normal subgroup is either finite and actually in the center of the group, or it is a finite index. There's a very nice generalization of this theorem, which is as follows. Every character of gamma is either finite dimensional, so it's like just the trace of a finite dimensional representation, or it is, let's say if it's center free, it's just the Dirac character. Two types of characters. It's quite amazing that this character rigidity actually is a strengthening of Margulis normal subgroup theorem, because if you take a normal, let's say you want to prove the normal subgroup theorem, you take n, a normal subgroup, and you take the characteristic function on n. This will be a trace on your group gamma. It means it's like a character, but it's still not indecomposable. But then you kind of do a Fourier decomposition. You decompose it to the extreme points, and then you use character rigidity. And you know that here you have this dichotomy, either finite dimensional or the Dirac. And then that will kind of give you whether the normal subgroup is finite index or finite. It's a very nice theorem. But then how would you get even, okay, this explains how do you get like normal subgroup theorem, but how do you get, for example, things about representation theory from this unitary representation, this wild theory, or about dynamics, etc. And here is the key point. If you have a representation gamma, a unitary representation, you can always cook up a function, a matrix coefficient function out of it. The problem is that this function is not conjugation invariant. Positive definite, but it's not conjugation invariant, so you can't really, it's not really in this framework. So you can't use character rigidity to obtain information about pi. However, what you can do is just average this phi, take random walks, and at the limit, you'll get some new positive definite function phi, which will maybe not be conjugation invariant, but it will be conjugation invariant in average. And then you want to prove kind of stiffness. You want to say if something is invariant in average, it should be invariant. So like, for example, here in SL and Z semi-direct product Zn, then you take this limit point and you restrict it to the radical, and you get a positive definite function on the radical, which is stationary with respect to this SL and Z. And then you do the Fourier transform, and you get a measure on the torus, on the dual, and then you get this dynamical system. We know it is stiff, and this is kind of how you proceed. So it kind of goes by the same philosophy of Tzachi Gelander's talks, that if you know things about stationary objects, it's much better than invariant objects. And the reason is because stationary objects are always exist. You can always just take averages and get a stationary measure. So we actually show that all stationary characters are genuine characters, and this is it.
Any questions for Itamar? Yes. They'll bring a microphone.
In the main theorem, you had a footnote saying that maybe it was not in the footnote, saying that you have stronger statements when gamma has property.
Oh yeah.
But of course, then amenability is ruled out. But do you get anything more?
What is ruled out?
Amenability.
Yes. So yeah, first thing, of course, is that wherever you say amenable, like you can upgrade wherever basically you see the word amenable, you probably can upgrade it to the word finite. That's one thing. But yes, even more. For example, here's a theorem I can tell you. I would say just a bit more. For example, IRS and URS, if you remember what that is from Tzachik talks, you can get that every IRS and every URS are finite. They're supported on a finite set. So you use slightly more than property T. And maybe this IRS here, I assume spectral gap. Suddenly you don't need to assume it. It's automatic, this kind of stuff, but quite conservative.
Any other question? If not, let's thank the speaker again.